Hi there, paragliding fans. Lift and Learn here, and today we're talking about something truly amazing: flight. Have you ever looked up at a bird soaring through the air and wondered, how do they do that? The answer lies in understanding the incredible properties of air. You see, air might seem invisible, but it's actually a fluid, just like water. It has weight, it can push and pull, and it's essential for everything that flies, from mighty airplanes to graceful paragliders. Just like a boat floats on water, paragliders float on air. But here's the thing, air isn't the same everywhere. As we go higher, the air changes, it gets thinner, colder, and less dense, and all these changes affect how things fly. So buckle up as we explore the fascinating world of air and how it makes paragliding possible. Let's start our journey by understanding how air changes with altitude. Imagine climbing a tall mountain. As you ascend, you'll notice that the air gets thinner. You might even feel a little short of breath. That's because the air pressure is decreasing. Air pressure is simply the weight of the air pushing down on us. At sea level, the air pressure is highest because there's more air above us pushing down. But as we go higher, there's less air above, so the pressure decreases. It's like a stack of pillows. The pillow at the bottom feels more pressure than the one at the top. Along with pressure, air density also decreases with altitude. Density is how tightly packed the air molecules are. At sea level, air molecules are closer together, making the air denser. But as we go higher, the air molecules spread out, making the air less dense. Imagine a crowded room versus an empty one. The crowded room has a higher density of people. Finally, temperature also plays a crucial role. As we ascend, the air gets colder. This is because the sun's heat is absorbed by the Earth's surface, and as we move away from the surface, the air gets progressively colder. It's like moving away from a campfire. The farther you are, the colder it gets. Now you might be wondering, how do pilots and paragliders keep track of all these changes in air pressure, density, and temperature? Well, that's where the International Standard Atmosphere, ISA, comes in. The ISA is like a standardized model of the Earth's atmosphere. It provides average values for air pressure, density, and temperature at different altitudes. Think of it as a handy reference guide for pilots and anyone else who needs to know about the atmosphere. Using the ISA, pilots can calculate things like air density, which is crucial for determining how much lift their aircraft will generate. They can also use it to estimate the performance of their engines and make sure they have enough fuel for their flight. Let's take a closer look at how pressure and temperature change with altitude using the ISA table. At sea level, the standard pressure is 1013.25 hectopascals, and the standard temperature is 15 degrees Celsius, or 59 degrees Fahrenheit. As we go higher, both pressure and temperature decrease. For every 1,000 feet of altitude gain, the pressure decreases by about 1 inch of mercury, or 34 hectopascals. Similarly, the temperature decreases by about 2 degrees Celsius or 3.5 degrees Fahrenheit per 1,000 feet of altitude gain. This means that at 10,000 feet the pressure would be about 700 hectopascals, and the temperature would be about -5 degrees Celsius or 23 degrees Fahrenheit. These changes in pressure and temperature have significant effects on flight, as we'll see in the following sections. Air pressure. It's not just about pushing down. Air pressure isn't just about the weight of the air pushing down on us. It also plays a crucial role in flight. There are two types of air pressure we need to consider: static pressure and dynamic pressure. Static pressure is the pressure of the air at rest. It's the pressure we feel when we're standing still on the ground or flying at a constant altitude. Dynamic pressure, on the other hand, is the pressure created by the movement of air. The faster the air moves, the higher the dynamic pressure. In flight, the difference between static pressure and dynamic pressure is what creates lift. The shape of a paraglider wing, called an airfoil, is designed to create an area of low pressure above the wing and an area of high pressure below the wing. This pressure difference generates an upward force, lifting the paraglider into the air. Air density, the key to staying up high. Air density is another critical factor in flight, especially for paragliders. As we learned earlier, air density decreases with altitude. This means that at higher altitudes, there are fewer air molecules to support the weight of the paraglider. To compensate for the lower air density at altitude, paragliders need to maintain a higher airspeed. This is because the lift generated by a wing is directly proportional to the air density and the square of the airspeed. So, if the air density is lower, the paraglider needs to fly faster to generate the same amount of lift. Pilots can also use something called thermals to gain altitude. Thermals are columns of rising air created by the uneven heating of the Earth's surface. Since warm air is less dense than cold air, thermals rise, carrying paragliders along with them. Temperatures influence riding the thermal waves. Temperature plays a crucial role in creating the thermals that paragliders rely on for lift. As the sun heats the Earth's surface, some areas, like dark fields or rocky slopes, absorb more heat than others. This uneven heating creates pockets of warm air that rise, forming thermals. Paraglider pilots are skilled at spotting and utilizing these thermals. They look for signs like birds circling in rising air or dust devils on the ground. Once they find a thermal, they steer their paragliders in circles, riding the rising air column higher and higher. Understanding how temperature affects air density and thermal formation is essential for paraglider pilots to maximize their flight time and distance. Viscosity, it's like air's thickness. Finally, let's talk about viscosity, which is a measure of a fluid's resistance to flow. You can think of viscosity as the thickness of a fluid. Honey, for example, has a higher viscosity than water, meaning it flows more slowly. Air also has viscosity, although it's much lower than that of liquids. Air viscosity increases with temperature, meaning that warmer air is slightly thicker than colder air. While the effect of viscosity on paragliding is relatively small compared to other factors like air density and pressure, it still plays a role in the overall drag and performance of the paraglider. Imagine sticking your hand out of a car window. The faster you move your hand, the more resistance you feel from the air. This resistance is partly due to air viscosity. Soaring high-how air makes paragliding possible. So there you have it, science fans. We've explored the fascinating world of air and how its properties make paragliding possible. From air pressure and density to temperature and viscosity, each of these factors plays a crucial role in determining how paragliders fly. By understanding these principles, paraglider pilots can harness the power of the air to soar to incredible heights, experiencing the freedom and exhilaration of flight. So next time you see a paraglider gracefully gliding through the sky, remember the amazing science at work. Keep exploring the world around you and never stop questioning how things work. And remember, science rules.